We are live. We are live.
Okay, welcome everyone to our last live seminar of OrbitCamp. And I am super excited to introduce our speaker, Dr. Varma. I can totally talk on Wednesday. Dr. Marva Carroll works at NASA's Jet Propulsion Laboratory in the Mission Design Group. She received her PhD from Purdue University, and while working at JPL, she has done a lot of work on a variety of missions, including one of my all-time favorites, Cassini, and is currently the mission design manager for NEO Surveyor, a space telescope that is going to find potentially hazardous asteroids. So Mara, thank you so much for joining us today. And I am going to hand it over for you. And for those of you who are watching us now, feel free to type your questions in the chat box, and we will have time at the end of this presentation to ask Mara some questions. Okay, take it over.
Thank you, Kayla. Thank you so much, and everyone else for inviting me today. Let me share my screen real quick. All right, so Kayla, can you confirm audio and visual? Can you see a full screen?
It looks great.
Okay, awesome. So thanks again, everyone. Welcome, and thanks for joining this afternoon discussion on cislunar trajectory design. with an emphasis on using multi-body periodic orbits as staging orbits for moon landers. So we're going to talk about one very specific application of periodic orbits. Before I get into the technical details, I'd like to acknowledge a couple of very important people in my life. My co-author here, Sonia Hernandez, collaborated with me in this work some time ago when she was working at JPL. Since then, she's moved on to other adventures, and she now works at Continuum Space here locally in Pasadena. And then also a quick shout out to my really good friend Juanma, who is watching us live from the Canary Islands, my hometown. Also, welcome everyone in the chat online. I can't get to see who you are, and I'm not going to see the questions until I'm done with the presentation. So if you feel comfortable, go ahead and drop a line in the chat window and introduce yourself, and maybe let me know who you are and what are your interests in space exploration. So Kayla mentioned that I am a staff member in the mission design and navigation section at JPL. I spend most of my time lately as the NEO Surveyor, mission design and navigation lead. NEO Surveyor is an infrared asteroid hunting space telescope set to orbit the Sun-Earth L1 libration point. We have a predicted launch date of March 23rd in 2026. So this is a really exciting mission. Pay attention to its development because the science is critical, really important, and just a really cool mission overall. And I'm also spending a little bit of time on Parker Solar Probe. I get to do navigation and flight path control for it, as well as Lunar Trailblazer, another small mission that we're currently developing, scheduled to launch next year, and also helping a little bit with a new concept to send a lander to the surface of Enceladus. So really, really exciting projects that we're working on. And this is a JPL-centric slide, so bear with me for a moment. But I do want to take a second to look back at everything that we've accomplished in the past few decades. So JPL spacecraft have visited every single planet in our solar system to date. Over the past 25 years, 5 rovers have explored the surface of Mars in coordination with a number of orbiters. Samples have been brought to Earth from both a comet tail and the solar wind. Saturn and its moons were studied extensively by the best mission in history. That was the Cassini mission. I would say I'm perhaps a little bit biased towards it. Planets have been discovered around neighboring stars, and this is a huge accomplishment in the past decade. And of course, many new insights into our planet's environment have been acquired. So we know a lot more of our own planet Earth because of all the assets that we have in orbit looking down towards our beautiful home. So what's our role as astrodynamicists? What can we do with some of our techniques to enable some of these missions now or in the future? Well, the idea, I think, in my opinion, the main idea is for trajectory designers and navigators to come up with techniques to allow exploration of the solar system using little to no fuel. This is the key, I think, in big part of the work that we do is to come up with ways to save as much propellant as possible. There's no gas stations in the solar system. Once the spacecraft leaves Earth, we got to make the most out of the propellant that we have on board. And of course, these techniques also have to keep in mind cost reduction at all times, and also risk reduction, which is literally everywhere when it comes to space exploration. Now, this is a super exciting time in astrodynamics. I'd say we are living in the golden age of astrodynamics, and in the coming years, many, many new opportunities will come up given the latest developments in launch vehicles and also small sat components. Smaller spacecraft are extremely capable these days because of the advancements in in engineering and in technology in general. So we can do a lot more with a lot less, or a lot smaller of a spacecraft. And we are going back to the moon. I think this was made really clear, was it 2 days ago on Monday, when the wet dress rehearsal for the Artemis booster, the launch for SLS, went really great, and it was a real success. So very soon, with the use of SLS, NASA's Artemis 1 test flight will take a big step returning astronauts to the moon. And I'm just gonna make this little comment for all of us to, again, take a moment and think of the magnitude of this change. This year marks half a century since the Apollo 17 astronaut Gene Cernan left the moon in 1972, and a lot has changed since then. Just to give you a tip, that same year, the first scientific handheld calculator was released. Today, we certainly carry way more computing power in our pocket than what was used to safely guide the Apollo astronauts to the moon and back. So we have, again, we can do a lot more with a lot less. And this is the current sequence of events that would take us back to the moon as currently planned. We have the Artemis 1 mission. Will take the new SLS mega rocket to send the Orion capsule on a roughly 4-week journey around the moon. This will be followed by the Artemis 2 mission in 2024, which will send astronauts around the moon and back. And then finally, the Artemis 3 mission will put astronauts down on the surface of the moon sometime around 2026, near the lunar South Pole, with the aid, of course, of the big rocket being developed by SpaceX, the Starship vehicle. Now, to get there, to get the humans to the surface of Mars in 2026, we're going to have to make a ton of cargo deliveries to the surface of the moon, which will include technological experiments as well as supplies. And here's the key of this slide and a good introduction to the rest of the presentation. Low energy transfers are extremely good candidates to support this task to get cargo to the moon frequently and cheaply. So what are low energy trajectories? If you've completed most of the modules in this wonderful course, then you will have heard of the 3-body problem, hopefully by now. So low energy trajectories are solutions to the gravitational 3-body problem, which does not have analytical solutions and is addressed by numerical analysis approximations. Now, a small number of exact solutions do exist, and these are known as the 5 Lagrange points or libration points or equilibrium points. Those are all interchangeable terms for this balance points. Low energy trajectories allow a spacecraft to change orbits using very little fuel by exploiting third-body gravitational effects. So this comes back to the point that I was making earlier about making the most out of the propellant that we have on board once the spacecraft leaves the vicinity of the Earth. So just to give you an example of a very well-known and studied and also flown low energy trajectory is the one for the Grail A or B spacecraft. So here's Earth, and then the orbit of the moon is shown in green. This was a JPL spacecraft that launched some time ago in 2011, so 11 years ago. And the idea here is to shoot out and go far away from the Earth-Moon system enough so that the gravitational effect of the sun makes a positive impact or change on the trajectory. So these trajectories are pretty cheap when it comes to delta V or propellant consumption, but they're also longer because we go out towards the sun and then come back again to the moon for landing or orbiting. These trajectories take longer to complete than, let's say, the alternate home and transfer to the moon. And because of the advantages that they have, they've been proposed in the past, and they're also being currently proposed to support a variety of moon orbiter and lander missions. So we're going to focus on the key of this presentation is to look at alternate staging orbits for moon landers. So we're going to focus on spacecraft that will land on the surface of the body. So what if things do not go as expected and the spacecraft is unable to land when and where it was supposed to? And what sort of scenarios am I referring to in this case? Let's think just have 4 examples here. In the case of a hurricane, we would end up with severe adverse weather that could cause a citywide outage of 3 to 4 days. Okay, so the spacecraft is on its way to the moon for direct landing on a low energy trajectory, and a hurricane hits town, and now there's no way we can proceed with the plan because of this outage of 3 to 4 days. Now it can get worse than that. Let's say we find a bug, a software bug, either on board of the spacecraft or in any of the spacecraft's 6 systems. Well, it would take us, we think, anywhere between 3 to 4 weeks to fix and test and uplink a fix to that bug. Flooding, this one's a bit of a doomsday, the next 2 examples, but let's say the JPL spacecraft operations facility where we control spacecraft from floods causing an electrical system failure that would take up to 1 month to fix it. So for 1 month, we're all scrambling, trying to get our bearings together, and we can't proceed with the mission as planned. And of course, the worst case scenario is an earthquake, which is not that uncommon in California, or a meteor strike, which would result in, God forbid, major property and life damage that could disable tracking and operations facilities for 3 to 4 months. So what do we do if one of these sort of scenarios happens and we can't proceed with the plan as expected? The idea behind the results that you're going to see in a moment was to develop a method to design abort trajectories for low energy landing trajectories that involved a direct approach to the moon landing location. So there's no orbit insertion involved to save propellant. And this go to airless bodies like our moon or Jupiter's moon Europa. So we wanted to have a backup plan in case something didn't go as expected. So here's an example of a reference trajectory that goes to an earliest body. In this case is the moon. So you have a departure from Earth, and then we ride on a low energy trajectory to the surface of the moon. This is an actual reference trajectory for Moon Diver, which was a discovery, one of the JPL discovery proposals last round. And the trajectory shown on the left in the Sun-Earth rotating frame. And then there's a close-up view of the landing phase plotted in the Earth-Moon rotating frame. So as you see, this trajectory comes in through the L2 gateway and then directly lands on the moon. Let me say that landing on the moon is not just a random selection or design. The location, the specific location on the surface of the moon was detailed and selected by the scientists. So we had really tight and specific constraints on the surface. So we need to achieve latitude, longitude, altitude, velocity, entry velocity, and also sunlight conditions. So we had a mean local solar time that we had to target at the arrival condition. All of this is not important in this discussion, but it is to say that we can't just land anywhere we want or, approach the moon however we get to it. We had to target very specific conditions that would only occur once a period, in this case, once a month. So if you're coming in, if your spacecraft is coming in on this trajectory and a week before landing, you realize that you can no longer land at the right time, you would have to wait an entire month to be able to achieve the same landing conditions that were initially planned. So some of the advantages of low energy transfers to the moon, I mentioned some of this a little bit earlier, but there's increased launch opportunities per month with a fixed arrival time and no variation in arrival conditions. And this is really powerful because with the addition of a maneuver somewhere during cruise, we can change the launch date, let's say varied by 15 or 16 days across a given month, and we can still target or achieve the same conditions at landing. As I mentioned earlier, these are really low delta V consumption trajectories, so they're very attractive from that perspective because we don't need to carry too much propellant to get to the surface of the moon. And the increased cruise time, some could view this as a disadvantage because you're spending longer time to get to the surface than you would following a home and transfer. But I see it as an advantage because it gives you plenty of time during cruise for in-orbit checkout operations or verification calibrations for your instrument, you name it. It gives you a lot more time to plan your arrival while the spacecraft is in cruise, during following the cruise trajectory. All right, so let's start with the simplest abort scenario that we can think of. So let me go back for a second. We're coming in on our L2 trajectory through L2, and we decide very last minute that something's not right. We cannot land. We have to abort the sequence, and we have to wait for a later opportunity. The simplest, very last minute option would be to perform what we call an abort maneuver. This could be done minutes before the entry, descent, and landing sequence to circularize the orbit to, whatever the altitude, safe altitude needs to be over the lunar surface. And then we would go into a staging circular orbit. And then N days after entering the circular orbit, then we would do a second maneuver, what we call the landing burn. In this case, it would be about a month later to retarget the original landing conditions when it's safe again to go into orbit. If we look at the total delta V cost associated with this change of plane, we come up with 806 meters per second, and this is prohibitively high, especially for small spacecraft that would simply take cargo to the moon, no humans on board. This sort of delta V is usually not available. Once you get close to the moon, you wouldn't have this much delta V left in the tank. All right, so what we propose to use instead are this parking orbits or periodic low energy orbits that exist in every 3-body system. We propose to use chunks or arcs associated with these orbits to come up with a cheaper option, abort option in terms of delta V. So we've selected a combination of 3 both 2-dimensional and 3-dimensional libration point orbits and distant prograde orbits, which are unstable and therefore possess stable and unstable manifold trajectories that naturally approach and depart the orbit. So we can use the stable mode if we want to approach the orbit, or we can use or exploit the unstable mode if we want to get out of the orbit. So these natural transfers, the manifold trajectories, make excellent candidates for low delta V abort options. So here's an example of orbits in the Earth-Moon system. These are the 3 orbits that I'm referring to and that we used in this study extensively. So we have an L1 Lyapunov orbit or a halo orbit. In the case of the 3, if we go to the 3-dimensional problem, and then we have another Lyapunov orbit around L2, and then we have a distant prograde orbit, or DPO, which circles the moon, and it's kind of embedded. It's embedded in between the L1 and the L2 orbits. And on the right side, I'm just showing the same structure or combination of 3 orbits. These are just at a different energy level. So these are different members within the family of orbits. So all we changed here was the energy level associated with the orbits, and you can see how the features are different. The orbital characteristics are pretty different. So how do we use these structures as staging orbits for abort solutions? We can, as I said, we can use parts or arcs of each of the orbit to form a parking orbit so that the spacecraft can safely hang in there until it's time to reattempt landing again. So here's just an example. I'm going to spare the details of how we came up with this particular trajectory design, but I'm going to highlight the values, okay, the numbers, and remember the last minute abort scenario that we use as a benchmark. And this analysis was 806 meters per second. So in this case, we can design a delta V abort maneuver for about 30 meters per second to get the spacecraft out of the direct landing trajectory. We send it into this distant prograde orbit for a number of revs. And when it's time to attempt landing a month later, then we design a delta V land maneuver for only 30 meters per second. And we get down to the surface at the same time at the right spot as initially planned. So the total delta V cost increase is about 60 meters per second, which definitely, or should not, jeopardize the mission overall. And in fact, it could be used from hopefully the fuel margin allocated for different contingencies. So do these structures or this sort of solution, are they unique to the Earth-Moon system? Is there something special about this trajectory that only existed around the moon? The answer is definitely not. The idea was to come up with a generalized method to find alternate landing trajectories, exploiting staging structures available in any 3-body dynamical system. So Sonia, in particular, studied the Jupiter-Europa system. At the time, we were both, we had done extensive work on the Europa lander mission concept. So we thought it was a great example to use as a, in a different system to show or demonstrate that the technique was equally applicable in a different system. So here's an very old version of a reference trajectory that we came up with for the Europa lander mission concept. This was years ago, and the concept changed quite a bit since then, but it still serves as a good illustration example. So the plan for this particular trajectory for the Europa lander mission concept was to get loosely captured at Europa. So here's Europa, and the trajectory is shown in blue, by entering through the L2 gateway. So the spacecraft was coming in from a resonant orbit around the Jupiter system, and then it came through the L2 gateway and got what we call loosely captured around L2. And then it kind of, you can see a resemblance again to that distant prograde orbit. It did one loop close to L1. Again, the landing conditions usually they're going to be pretty specific and detailed ahead of time. And mostly none of these parameters, except for the inertial velocity at arrival, can be changed. So in this case, we had an arrival, a very specific solar local time on June 13th, 2032. And then we had a specific set of orbital elements that we were targeting right before landing. So we had an altitude, a latitude, a longitude, flight path angle, and azimuth. Those specify the direction the spacecraft comes in towards the landing site. And then we had designed 2 delta Vs. This first maneuver was to reduce the energy of the spacecraft. And then the second maneuver was to place it to nail or target the final landing trajectory. So in this study and the results that you're going to see in a moment, we simplified the arrival a tiny bit to make it a little easier to follow from a research perspective. So for this analysis, we assumed that delta V1 to get loosely captured around Europa had already been executed. So the spacecraft had done this delta V1. And what we did was ignore delta V2 because something doesn't go according to plan. So we can no longer land at the time we wanted to. And we redesigned the sequence after the first maneuver. So here's the sequence that we considered in this study. We considered 3 different abort scenarios for the Jupiter Europa system, and all 3 exploit different combinations of the proposed multi-body staging orbits. So the delta V abort maneuver places the spacecraft on one of the 3 periodic orbit structures. It could be an orbit around L2, another Lyapunov orbit, or Lisieux orbit, or a halo orbit, some periodic orbit around L1. And then for the center portion, we considered the DPO, the distant prograde orbit. Now, once the first maneuver is executed, the abort maneuver, then the spacecraft can remain indefinitely orbiting the staging orbits until conditions are adequate again to perform another attempt, to attempt to land for a second time. Now, once we are ready to send the spacecraft down to the surface, then we can perform a last maneuver, delta V land, which will place the spacecraft on a direct landing trajectory to the same location as the nominal trajectory. We considered both options. So we looked at optimizing delta V, try to get down to the surface for as little propellant usage as possible, or we also consider getting to the surface as fast as possible. So minimize time of flight, even though this usually results in an increase in some sort of delta V penalty. But what we know and what we did make sure is that the exact arrival conditions were guaranteed some time after the decision to abort the nominal landing. All right, so we came up with a plot like the one you see on the left, where we look at staging or revolutions along a given staging orbit. So in this case, we looked at how many revs do we need to go around, how many times orbits around the L1 orbit before we can get to land. And on the y-axis, we see the timing offset from the required landing conditions. So I mentioned that the local solar time was really critical to get down to the surface when the lighting conditions were specific. And so ideally, we're looking for points on this red line. This means that if there's a point like this one, for example, if there's a point right on the red line, then we know that we are getting down to the surface exactly at the same landing conditions as we had considered initially, but just n number of orbits after we get into the staging orbit. So this sort of plot was really useful to identify quickly how many revs we needed to design for before reattempting landing. However, for this particular mission concept, we had to deal with a really terrible radiation environment. Europa is within the radiation belt at Jupiter, so the spacecraft wouldn't survive too long without getting baked, basically, by the radiation environment. So we thought that having to wait for 15 revs would maybe not be an option without getting the spacecraft components damaged by the radiation environment. So we had to look at a faster alternative to get down to the surface. So we created a slightly modified version of the plot where we look at the number of revs on the x-axis, but then on the y-axis, we look at the cost in meters per second that it would that we would need to apply to get down to the surface faster. So in this case, we have the original example where we wait for 15 revs and we basically get down to the surface at no cost, or we could get down to the surface, try to get down to the surface after 6 revolutions around the staging orbit, apply a delta V of 47 meters per second and achieve the same landing conditions as before. So we shorten the time of flight by spending a little bit of delta V, but this is still not a large cost by any means. So here's a slide that summarizes that the 2 options that we considered for the Europa lander mission concept. So the first option is to maintain the orbit energy. Then we wait in the selected staging orbit for 4 weeks, which are more or less 15 revs around the libration point orbit. And then we get down to the surface at no cost, effectively a delta V of about 0 meters per second. The second option is to increase the energy of the staging orbit, wait for half of the time, so 2 weeks, or 6 revs around 01, and pay some delta V cost to achieve the same landing conditions, but get there faster. So both are options, or both were viable options and a lot cheaper than having to go into a low altitude orbit above Europa. Like if you remember that initial example, the last minute abort example where we circularize the orbit and spend lots and lots of propellants, anywhere from 800 meters per second to even 8 kilometers per second. All right, so I gave you a lot of information and not that much time about one particular application of low energy trajectories. In this case, we're using them we're proposing to use them as staging orbits in case something doesn't go according to plan and the landing cannot be attempted as initially intended. We looked at 2 cases in detail. One was in the Earth-Moon system, and the other one was in the Jupiter-Europa system. And these are examples that were directly applicable to proposals or concepts that we were looking at JPL back in the day. And this were a moon diver in the Earth-Moon system and the Europa lander mission concept. But we're confident that this method could be applicable to other missions in different 3-body systems. So what's the takeaway of this presentation? If I want to remember something when you walk out of this quick seminar, is that this type of orbits, low energy transfers that exploit periodic orbits and the manifolds associated with them, appear to be really good abort mechanisms that reduce propellant cost if a backup landing opportunity is needed. We even talked about the possibility of including some number of reps into the initial reference trajectory design so that you don't have to scramble last minute and try to come up with a new design to get into a staging orbit if something doesn't go according to plan. Now, if you do design it from the beginning, from launch, you include some sequence of periodic staging orbits into your design, it's very likely that the delta V goes significantly down if you're able to optimize your entire trajectory to include them. The downside to it is that if everything does go according to plan, there's really no need to have the spacecraft hang out around L1 or L2 for no specific reason. In this case, you might want to just get to the surface. So there's a bit of a trade-off there, to save propellant and reduce risk, which are the key points that I made in one of my first slides. As trajectory designers, those are the two most important things that we need to keep in mind: reduce cost, reduce LTV and risk. Or, the scientists will say, we're ready to go, we're ready to land. Why spend time hanging around the libration points if it's not needed? But know that these are options that you can use as trajectory designers now or in the future to add robustness to your design. So that's all I had to cover in terms of content. We have plenty of time for questions and discussion. So I'll let Kayla or Davide take it from here.
Yeah, I'll take it. Thank you, Dr. Bakir, for the presentation. I think it was very inspiring, and I especially enjoy your example on how subsystem constraints or requirements, such as when maybe environment requirements, such as radiation, impact trajectory design. Sometimes it's not just about the delta V. There are other considerations that comes into play when you work on real problems. So I'll go ahead and relate to you some questions that were posted in the chat, and I think I'll start with this one. Was the work that you presented relies in the circular restricted three-body problems or in ephemeris? And when you design a methodology or we design a sequence of staging orbit in the circular restricted three-body problem, which is a simplified dynamical models, how do you compensate for errors, for modeling errors that naturally occurs when you transfer to ephemeris?
That's great. Yes, that's a great question. And the answer is a combination of both. So in the example that you saw in the Earth-Moon system, I did the design completely in the ephemeris model simply because the tool was readily available or readily designed to do that. So I was able to quickly come up with an orbit from the Poincaré catalog, which is now available to the world. So just grab an orbit from the catalog and then propagate it in the ephemeris model with the appropriate constraints and had no issues with that transition. So the Earth-Moon example was done entirely in the ephemeris model, but the Jupiter-Europa system was done entirely initially in the circular restricted three-body model. So we had an ephemeris trajectory to begin with. That was the Europa lander mission concept reference trajectory, and that was, of course, designed in the ephemeris model. So we went from the ephemeris model to an approximation of the circular restricted three-body problem. Then we chose the periodic orbits that best fit the energy level, the approximated energy level from the ephemeris trajectory, did the entire design, the three-body were the same in the ephemeris model. So it should work, the method should work in any system. Of course, you have more freedom in your design if you work in the circular restricted three-body problem. You can choose different orbits and different energy levels. So that would be my recommendation, to start with the basic model first, and then do the transition to the ephemeris model at the very end for verification purposes.
And kind of building on top of your answer, and I'll tag another question along. Yeah. Could you speak a little bit about periodic orbits and how periodic orbits are different from quasi-periodic orbits? Now, we don't cover quasi-periodic orbits in the camp. I do not believe we do, but someone apparently is aware of what quasi-periodic orbits are, and it's very interesting in learning more. So.
Yeah, so quasi-periodic orbits are, it's exactly what the term tells you. It's an orbit that remains bounded close to the original periodic orbit, but doesn't quite return back to the same point. So in reality, periodic orbits exist only in the theoretical model. In the circular restricted three-body model is where we can design or specify periodic orbits. In the ephemeris model, when you take into account additional perturbations from other bodies, or you include the real orbits, they're not circular and coplanar anymore, then that periodicity factor goes away. And the best you can do is come up with a quasi-periodic orbit that it does resemble quite a bit the periodic orbit. So in practice, in trajectory design, for some of our concepts and our missions, we work entirely with quasi-periodic orbits, but we always start from that first periodic orbit to do the initial analysis. And then once you start applying constraints or reality to your trajectory design, then you'll see that periodic behavior morph into a quasi-periodic behavior. And then there's one more thing, there's quasi-periodic orbits also defined in the circular restricted three-body model. There's quasi-periodic halo orbits, Lissajous orbits, and when you transition these orbits into higher fidelity models, they become just a tiny bit more quasi-periodic, but those also exist in both models.
And so Yuji Takubo, and please forgive me if I mispronounce your name, is asking, how do you decide which orbit, halo, retrograde, prograde, etc., as well as what energy level around the moon to be chosen as the abort orbit? Essentially, how do you choose your staging orbits, and if there is any heuristics that you are leveraging?
Mm-hmm. Excellent question also. So if you want to minimize the delta V penalty or the propellant penalty associated with changing your plan, you want to choose an orbit, a staging orbit that is as close as possible to the energy of your incoming reference trajectory. So you have to think about what kind of orbit you are writing to get to the moon, study that orbit in terms of whatever characteristics that orbit has, and then the energy level. And from there, you're going to choose from a variety of orbits, periodic orbits that are available to you. Like I said, these are families of orbits, so they have infinite number of members in them. So you're going to choose the orbit from the family that matches as best as you can the energy level associated with your incoming reference trajectory. That will minimize delta V. But if your constraints are different or your intent is different, and let's say you have like propellant for some miraculous reason is not one of your problems, then you can choose different orbits. That would be very problem dependent. But I would say energy matching is what you're looking for initially.
And how many trajectories do you design for a specific mission? And I will clarify this question. What this viewer is asking, do you try to have all the options available ahead of time, or you run scenario closer to the event? Or
that's
both?
Right. No, that's right. The more trajectories you look at, the better you understand your system and the more robust your design is. As a trajectory designer, my biggest nightmare is not finding or feeling or thinking that I haven't found the most optimal, the best trajectory for my mission. As you know, there's an infinite number of trajectories out there. There's an infinite number of options to get from point A to point B. And this is, it applies to everyday life and everything we do. You're going to depart from A, you're going to get to B. The ideal would be to get from A to B in the most efficient possible way. So how do you find that? And there is no, as you know, trajectory designers in the forming or experience, there's no way to know. There's no global best possible trajectory for a given problem. So the more trajectories you look at, the more convinced you'll be that your design is robust enough to changes and the best that you can do to save delta V, save propellant for the mission, and reduce cost. So it depends on the mission, how long you have to come up with a design, and also how far along that design is in the process. So for Neo Surveyor, for example, I have it right here. This is the 3D model of Neo Surveyor. It's a telescope mounted on a spacecraft bus. Has, high gain antenna, low gain antenna, and then a big sun shield in the back to protect the telescope. Neo Surveyor, it's going into a halo orbit. So we've computed one halo orbit per day on a given year for the launch period, the 1 year that we're considering to launch in. We've looked at northern halo orbits, southern halo orbits. We've looked at Lissajous orbits to see if they are a better option to meet the constraints and to be a altogether better trajectory for our mission. And we decided to settle on northern periodic halo orbit for our mission. Is that necessary? It depends. It depends on, again, how robust you want your system to be and how bulletproof you want to be in front of a review board, which will question your entire design top to bottom. So you want to show that you understand the design space. And the only way really to do that is by studying different options.
And since we're talking about the robustness of a trajectory, Marco Lombardo is asking, how can you deal with statistical delta V in a low energy trajectory? So in the multi-body problems, are statistical delta V different from interplanetary trajectories?
Yeah, for
and
sure.
Marco was asking about launcher injection covariance, but I guess there are also other reasons why you have statistical delta V.
Absolutely. So your initial injection covariance will give you an idea for how bad the injection errors into the cruise trajectory can be from the launch vehicle. So, the launch vehicle is not going to put you on the right trajectory perfectly. There's always going to be errors associated with the injection. So you account for that source of error initially. You look at maneuver execution errors. So the spacecraft has 4 TCM thrusters, Neo Surveyor at the bottom, but these thrusters don't thrust perfectly. There is an error associated with each time we do a burn. There is an error associated with the thruster system because nothing is perfect. So you include those into account. Then you have orbit determination errors. We don't know exactly with precision where the spacecraft is in space. So we account for possible errors in mismodeling and the different effects and factors that go into the model. So all of these are no different than the errors that we consider for interplanetary spacecraft. However, the effect of these errors are a lot larger on low energy trajectories than they are on let's say a cruise trajectory or home and transfer to Mars. And why is that? If you remember, we're talking about the stable and unstable manifolds associated with these trajectories. These are natural flow trajectories in and out of the orbit itself, which means that if you apply a tiny bit of a maneuver, a little change of velocity at the right time on the right location, that trajectory will take you really far away from your orbit. So these errors that we deal with during flight, from maneuver execution errors, orbit determination errors, can act as tiny little maneuvers applied on the trajectory. So if we don't account for them properly and constantly, we could fly out of the halo orbit very easily in 3 to 6 months, depending on the period of the system. And it would take a lot of delta V and effort to bring the spacecraft back to the reference trajectory. So I tell people in the Neo Surveyor project who are not trajectory designers or don't know much about low energy trajectories, we are getting to the Neo Surveyor is getting to its final halo orbit for free. We're writing a stable manifold onto the halo orbit, which means if the model is perfect, We don't need to apply any maneuvers to get to the orbit. That also means that we're getting out of the orbit for free. So if there's any small errors that are accounted for, the spacecraft will depart. Same as it gets to the orbit for free, it will also depart the orbit for free. And that's why station keeping maneuvers are so important for some of these orbits, like halo orbits, extremely important to do periodic, very small corrections, but periodic enough to maintain the spacecraft in the right orbit.
And so, since we're talking about navigation errors and station keeping, tracking the spacecraft along its orbit, one of the viewers asking, and after one studied trajectory optimization, he or she should be also familiar with navigation like Kalman filter to work for NASA. And let me know if I need to repeat the question because my connection went away for a second.
Yeah, I think, do
so
you mind?
Essentially, is navigation important to work? Yeah.
Yeah, you cut out a little bit. Do you mind rephrasing the question?
The question is if it's important to be familiar with navigation and orbit determination techniques such as Kalman filtering to work for JPL or NASA. And I will tag Edward questions along. And Edward was asking how orbit determination and Kalman filtering is important in NEO Surveyor.
Critical, yes, critical. Is of critical importance. And so the way we work at JPL in the mission design navigation sections, we have, let's keep it really basic. It's a little more complicated than this, but we have essentially three different groups of engineers within the mission design and navigation section. So we have the trajectory designers or the mission designers, the navigators or the orbit determination analysts, and then we have the flight path controllers or the maneuver analysts. So as the titles clearly say so, trajectory designers are mostly focused on coming up with that reference trajectory, which is perfect, exists in a perfect world. It could be ballistic or half deterministic maneuvers, but they come up with the trajectory that we intend to follow and that we're never going to follow once we get into orbit because the models are not perfect. So after launch, then the navigation team takes over and is in charge of flying the trajectory and making sure that the spacecraft stays as close as possible to that reference trajectory. So the navigation team traditionally split between orbit determination analysts and maneuver analysts. So if you want to maximize your chances, experience, and knowledge, you want to know a little bit about everything. You want to understand how a trajectory is designed. You definitely want to understand how a maneuver is designed and executed. And it would be great if you knew how to find out how to find the spacecraft in space. But traditionally speaking, you're going to have one area of expertise. You're going to be really either a trajectory designer, a navigator, orbit determination, or maneuver. The more you know, again, the better engineer you are in general. But yes, absolutely, each component within this big section, the big group, has a critical task to carry out at JPL within the mission design and navigation section.
And so I'll circle back to the beginning of your talk and ask one last question before we wrap up, which has to do with optimization and computational power. So I'll try to rephrase the question that was posted a little bit. The question goes as, how optimal are trajectories that are selected for actual missions, or they are quote unquote just feasible? And this is asked in light of limitation of numerical integrations and limitation in computational times, or the time that will take to explore all the optimal solution.
Right. Yep. And the answer is neither of those. The limitation is the science team. So the scientists are usually the ones that make a trajectory not optimal, not perfect. So as trajectory designers, we come up with the best possible trajectory, hopefully, to get to your destination. And then the science team looks at it. Remember, everything we do is for them. Everything we do at JPL is for science and to be able to achieve a number of goals. And so if you, let's say you design a flyby sequence to explore parts of Europa, and you know your flyby has a close approach because the trajectory is optimal the way you design it, has a close approach above a particular point that they don't care about. They don't care about that latitude and longitude in Europa. They care about, again, a different location, different orientation, different lighting conditions. Then your trajectory will probably no longer be as optimal as you initially designed it, but it does meet a number of scientific requirements. So it's a really careful balance between satisfying the mission constraints and science objectives while minimizing fuel and resources in general. So it can go either way. Maybe for a neo surveyor, for example, because of the scientific objectives are not that dependent on the orbit the spacecraft is in, then we had quite a bit of freedom to choose the perfect orbit for this spacecraft. But if you think of Europa Clipper, that trajectory is entirely tailored to specific passes over the surface of Europa to create a complete map of the moon. And so the trajectory is going to be entirely tailored to the needs of the science team. And then in addition to that, in some cases, it is optimal to put a maneuver at the closest approach. Let's say if you have a flyby trajectory, you're going to get the most impact or benefit by doing a burn as close as possible to the body. But guess what? That's where the best observations are also taken, at the closest approach about the moon. So usually in the case of the Cassini mission, the navigators were not allowed to perform a burn within 6 days of the closest of the flyby of Titan in this case. So we could do the last correction burn was done 3 days before the flyby, and then a cleanup maneuver was done 3 days after the flyby. So they basically had 6 days of quiet, no vibrations, no thrusters, nothing affecting the trajectory, so that the instruments can point towards the surface of the planet and take those really valuable measurements for scientific purposes. So you have to work with them. You have to work with the scientists very closely.
Absolutely. Yes, absolutely. So I think let me relay our warmest thank you from our Orbit campers. Thank you for taking the time to joining us today. I think it was a very exciting discussion, and I think we've learned a lot from you today. So thank you, Gay, and thank you to all the viewers and Orbit campers. I hope you enjoy what you're learning. See you next time.